I'd like to go through Venn diagrams and Karnaugh maps and how you can apply them to a question. This question comes from the probability review notes from Miss Kirk, and it's question number 4. So suppose the probability that Gavin will be fit to play in football in the next game is P. If he plays, the probability that his team will win is 0.6. If he doesn't play, the probability that the team will win is 0.3. The question is, if the probability that his team will win the next game is 0.5, what is the probability that Gavin will play in it? If you haven't had a shot at it, maybe pause it here and have a go yourself. So this one, the first thing that we need to do is start putting our information into mathematical notation. So we start off with G for Gavin playing. So the probability of G is P. So the probability that he doesn't play is G dash, which is 1 take away P. The probability of winning with Gary, given that Gary plays, is 0.6. So that leads to our formula of the intersection of those two things over the probability of Gary playing. And you'll see there that we have this ability to multiply that P across to both sides and get an expression for the probability of W intersection G, 0.6P. This is quite common in these problems, where we're given a letter to stand in place of a probability, where we have to make up a number of expressions. The same way I figure out an expression for W intersection G dash, and I get 0.3 times 1 minus P. Our question was asking about the probability of winning, so I better come up with an expression for that, and I can do that by adding those two expressions together. If you look at the Venn diagram there, W intersection not G and W intersection G are represented by that red and green area. Add them together and you get all of W, where Gary's not playing, winning where he is playing. Add them together and I get a new expression for W, 0.3 plus 0.3P. So we're told that that was equal to 0.51. I can just substitute that in and solve it to answer the question. And so I get that the chance of Gary playing was 0.7. The question itself was a bit of a tricky one because it kind of suggested that there was going to be a conditional probability in that final bit, whereas the only conditional probability was earlier on. I want to have a look at this problem a little bit deeper, in particular how you could represent some of the other sections of the event space. So we're going to use a Karnaugh map. Now don't forget we write G and G dash up the top, and down the very bottom row there I've got the probability of G is P, and then I can do 1 take away P to get the probability of G dash. That's true of all the rows and columns. The two values in the middle have to add up to the value at the end of that row or column. And of course I can use that if I can get one of the other values in a row or a column. So earlier on we figured out that the probability of W given that G, the probability of winning given that Gary was playing, was 0.6P. And we got an expression for the probability of winning without Gary playing, which was 0.3 times 1 minus P. Now since we've got those two values, now those two values in the top row will add together to give the total probability for W. Likewise, my 0.6P plus that missing value below it is going to add up to a total of P. So with a subtraction I can figure that out as well. That allows me to start filling out other missing values in the Karnaugh map. I can finish off that last column by subtracting from 1 the 0.3 plus 0.3P, and now my values are all filled out in the Karnaugh map, which enables me to answer lots of different types of problems. To represent these sections of the Karnaugh map, I would be looking at the Venn diagram. So the green area there is W intersection, not G. The blue area in the middle of 0.6p is W intersection G. The red area is my not W, not winning, with Gary playing, is 0.4p. And then last but not least, outside we've got not winning intersection, Gary not playing. So those four areas, A, B, C, D, those are represented on your Venn diagram and match up with those corresponding sections in your Karnaugh map. And of course, if we add sections B and C together, we'd get the total amount of probability for winning, which is represented by the end of that very first row. Likewise, if I add C and D together, I'd get the total probability of G, which would be adding that first column together to get a total of P, and so on. So by combining different parts of that, you can come up with other probabilities of interest.